In this video, we are going to discuss limits at infinity and horizontal asymptotes. For people who have taken pre-calculus, this would seem a little bit familiar because if you remember talking about the end behavior of a graph or the end behavior of a function, we are doing that same topic based on calculus. So we'll have some of the graphing component that you would have done in pre-calculus, but our focus will be more on the equation aspect instead of the graph aspect. Of course, with absolutely everything, you could always plug this into a calculator and look at the graph to help verify your algebra. Completely valid strategy, though we will not take the time to do it in class. Our learning objectives are fairly straightforward. Evaluate a limit as x approaches infinity. And using limits at infinity will determine the end behavior and horizontal asymptotes. So starting off, before when we were looking at limits, we always did limits like x approaches 2, where it was approaching some finite number. And we were able to do just direct substitution then, saying for this limit, because it's continuous, 2 cubed would say it's going to close in on 8. How is it different to say approach infinity? The big difference is when we're looking at a graph like this for x cubed, we are no longer saying with this section what's happening when x is approaching 2. We're saying as you get farther and farther out to the right for positive infinity, what is happening to the y value as you go farther and farther right on the graph. Well, for this one, we know it's going up and up and up and up and up, so we should be able to say that's going to go to positive infinity. And likewise, if we said we're going to the left, left and left and left and left for approaching negative infinity, well, the graph is going down, 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 so we would say negative infinity. Well, we know that not all graphs go up to infinity or down to infinity. When would you be able to recognize if they tend to level off? So this part, limit as x approaches infinity, f of x equals 5. Well, if we're talking about it being equal to 5, 1, 2, 3, 4, 5, we're saying as we go farther and farther and farther to the right, our graph would need to have something that's perhaps doing this, closing in on it closer and closer and closer. Where you can see I've already done the dotted line for a horizontal asymptote. Here's the calc definition for a horizontal asymptote. If you take a limit going to positive infinity, or if you take a limit that goes to negative infinity, but it will equal some finite number L, that's how you can recognize horizontal asymptotes. We'll just need to evaluate a limit. Since it's all about evaluating limits, here's a graph. What do you know? Infinite limits refer to the x values that go up to positive or negative infinity. So what are the infinite limits? Okay, infinite limits are the vertical asymptotes, where it's going down to negative infinity or up to positive infinity. So the infinite limits are at x equals -1 or x equals +1. Looking at the limits at infinity, this is saying as x is approaching positive or negative infinity, what's happening? Well, as x is going farther and farther and farther out, it's closing in on this horizontal asymptote. So we could say the limit as x approaches infinity is going toward y equals 1. You'll note that's the horizontal asymptote. And the values we had before were the vertical asymptotes. basically our horizontal and vertical asymptotes are entirely dependent on the idea, when does x go off to infinity, what happens, and when do you have y going up or down to infinity or negative infinity. So here, evaluate the limits. What do we have? Perhaps the easiest way of thinking about these is to start using some actual numbers. If we are taking x approaches infinity, that means our x values are getting bigger and bigger and bigger. So we could create a sequence like 1 over 10, 1 over 1,000, 1 over 1,000,000. And if we kept plugging in bigger and bigger and bigger x values, what's happening to it? So we're going from 0.1 to 0.001 to 0.000451. What's it going to? 0. A really nice little trick. If you are starting to encounter in a limit 1 over infinity, infinity, just remember, really huge numbers. You divide by huge stuff, you get 0. Well, what if we change it so that we're approaching negative infinity? Well, let's start bringing in negative numbers. So we have negative, negative, negative. What is it still going to? In both of these instances, they're both going to 0. This fact we're going to use a lot. If you have a constant over something approaching infinity, it's going to start going down to 0. No, not 0 on this one. Well, we just saw that if you're taking the limit as x approaches 0, or as x approaches infinity of 1 over x, that's going to go to 0. We'd like to take advantage of that and take this piece and start splitting it up into a huge amount of limits. And so here's what we're going to note. The biggest exponent we have anywhere here is a 2. So what we will do is take every single term and divide by x squared. When we rewrite this, essentially what we're doing is taking this limit and having 5x squared minus 3x plus 1 over x squared all over 8x squared minus 2x plus 4 over x squared. You'll note the algebra, just x squared over x squared, doesn't change it. But that allows us to rewrite this whole piece. X approaches infinity. 5x squared over x squared minus 3x over x squared plus 1 over x squared over 8x squared over x squared minus 2x over x squared plus 4 over x squared. Where are some pieces that simplify? X squared over x squared cancels completely. Same thing there. X over x squared would cancel to be just over x, and there as well. So we wind up with this piece where we have the limit as x is approaching infinity, 5 minus 3 over x plus 1 over x squared, 8 minus 2 over x plus 4 over x squared. And all we've done is some algebra to rewrite the piece. What do you notice? What are each of these terms going to? What's the limit of 5 as x is approaching infinity? It's just 5. But 3 over infinity, or 3 over approaching infinity, that's 0. If you're taking x squared, well, really huge times really huge is going to be really huge. So this is still going toward 1 over infinity, so 0. 2 over x is going to 0. 4 over x squared is going to 0. So what is this thing approaching? 5 over 8. We have our answer. The algebra, you look at that and say, wow, that's a lot of algebra. And yes, we do expect you to be able to write up the algebra like this, but I'd like to show you something really, really quick. X squared over x squared, paying attention to the largest exponent in the numerator and the denominator. Do you notice how the powers are the same? 2 matches 2. Because the exponents are the same, what do you see for the limit? This only works when the exponents are the same. Only works basically when we're talking about having a rational function, a polynomial over a polynomial. But that's a pretty slick shortcut if you know it. The question was, would you have to show all this work? You should definitely know how to write up the work, because a lot of this strategy will still apply to other problems as well. But if you would like to be able to say, this is a very well-known property with rational functions, and so yes, you would be able to use it. It's okay, and you would be able to not have to show all the work, but please keep in mind, not all of them are quite this straightforward. And you do have to pay attention to the exponents, and we will have some other problems that we'll look at when the exponents are not the same. How does it change the problem? We'll see a couple more of those in our examples coming up. For example, here, find the horizontal and vertical asymptotes of He graph of the function. Okay, so where do vertical asymptotes come from? Vertical asymptotes, remember, generally come from dividing by 0. So when 6x minus 1 equals 0, we're likely to have a vertical asymptote. So that tells us x is equal to 1/6. One thing that we should be aware of, though, and should check quickly, if we have a removable discontinuity, we won't have a vertical asymptote. So does this number 1/6 also make the numerator equal to 0? If it makes both the numerator and denominator equal to 0, we would need further investigation. Well, let's just check quickly. Does 1/6 make a square root equal to 0? No. Because this does not make our numerator equal to 0, we would have our vertical asymptote, and we're done. We still need a horizontal asymptote, though. Horizontal asymptotes are going to come by taking the limits at infinity. So 4x squared plus 1 over 6x minus 1. A lot of times we would like to be able to just do a direct substitution and say, well, what happens? If we wind up with like 5 over infinity, we know what happens. If we wind up with infinity divided by 2, well, infinity divided by 2 would still be going off to infinity. So direct substitution you could try, but a lot of times it will not work. Infinity squared times 4 plus 1. Well, basically we can look at this and see the square root of infinity. Still going to be infinity over infinity. Well, infinity over infinity doesn't make any sense whatsoever. We can't just go through and say, oh, it's 1, or it's 5/8, or it's anything. Because infinity, remember, is not a fixed solid number. This is a piece that will require more investigation. If you get 0 over infinity, that doesn't make sense. If you're getting infinity over 0, if you're getting infinity over infinity, basically, if you're getting a number of different forms, you need to do some further investigation. Well, I'd like to ask you, What is your suspicion for what we need to do on this particular problem? Okay, idea the class had, multiply by the square root of the conjugate. Okay, so let's take the class's idea for their intuition and say, what do we get? Okay, so square root times a, we know with a square root times a square root, it's going to stay a big root. But then when we're looking at 4x squared plus 1, 4x squared minus 1, well, as a difference of two squares, we would have 16x to the fourth minus 1 all over 6x minus 1, 4x squared minus 1. Okay, so what's happening now? If we are looking at this from an intuitive approach, if we're taking x approaching infinity, if we start getting really, really far out towards like 10 million, 100 million, and farther, is there much of a difference between 16x to the fourth and just 16x to the fourth minus 1? All this minus 1 is doing is shifting it down 1. So if you're getting really, really far out to the infinities, this is a piece that we would look at, and very intuitively, we're saying that's basically 16x to the fourth. Because out near infinity, they're really not that much different. Same thing in the denominator. 6x minus 1, if you start putting in numbers that are near like 100 trillion and farther, that minus 1 really isn't doing much. So basically, in terms of limits, that's near 6x. And that root is also really close. The minus 1s near infinity don't do much, because frankly, what's infinity minus 1? That's infinity. So this is a piece that we could try to simplify, very touchy-feely intuitive. What's the square root of 16x to the fourth? Four x squared over 6x times, and then the square root of 4x squared, 2x. So what winds up simplifying? X squared over x squared. So 4 over 12 is 1/3. And we're happen to be done. I'd like to show you sort of a quick way of touchy-feely, intuition-wise. What is the square root of that? What do we wind up getting? All right, so what is your intuition? What would we want to do here? Okay, one of the students said square root of 2x squared plus 5 in terms of sort of a touchy-feely approach. We know the plus 5 near infinity is not going to do much, so basically we're looking at that. And so we're saying the square root of 2x squared would be just the square root of 2 times x minus x. And again, very, very touchy-feely. This is not proper calculus, just so that you're aware. We're being a bit sloppy here. The 5, we pretty much just eliminated, because if you're talking about going outward to infinity, a plus 5 vertical shift when you're talking about being near infinity doesn't really do much. I mean, again, it's like infinity plus 5, because if we're trying to do a direct substitution here, square root of 2 times infinity, well, that's infinity. Infinity plus 5 is infinity. Well, if we're trying to direct substitution here, We're getting infinity minus infinity. This is one of the things that you've got to be very, very careful about. Infinity minus infinity does not make sense. Because remember, we're talking about massively huge minus massively huge. We don't really have degrees for massively huge. Infinity minus infinity does not equal 0. One of the things that we could do, though, in terms of looking at this particular spot, what if we were to factor out the x? Well, in this instance, we're then basically looking at infinity multiplied by some finite number. And this finite number, remember, square root of 2 is approximately 1.414. So this piece is about 0.4. What's infinity times 0.4? That's still infinity. So in this instance, this is showing that we can't take infinity, subtract infinity to get 0. It actually turns up this one is still infinite. So if we were to graph this particular function, it's still going to wind up going to an infinite height as we go farther and farther to the right. I would like to note, though, that piece that we were doing, very intuitive, very touchy-feely, very sloppy. If we wanted to show that same type of piece more efficiently, the technique we could have used is the conjugate. If we multiplied by this conjugate, we would have had the limit as x approaches infinity of 2x squared plus 5 minus x squared over this root plus x. And so what we wind up with is 2x squared minus x squared is just 1x squared. And so then we're looking at this piece of x squared over further. We would be able to do a divide by x squared component from here and say x squared over x squared all over 2x squared plus 5 plus x over x squared. I'm running through this very quickly because we're not going to finish the entire problem. But then this would be 1 over, and then we'd need to show that this denominator is going to wind up going to approaching 0 from the right. As this approaches 0 from the right, 1 divided by progressively smaller numbers balloons upward toward infinity. But we could go through and do a conjugation technique to have some rewritten components. Okay, what about this one? Cosine of 1 over x. Well, cosine 1 over x, we're basically trying to think of this in terms of a direct substitution. And again, the pieces I'm writing, this is saying we're basically looking at cosine 1 over 0. What's happening with 1 over infinity? 1 over infinity is basically going to 0. So we're looking at this and thinking intuitively, it seems like it should be going to cosine of 0. Or at least in the limit, it should be approaching cosine of 0. What's the cosine of 0? 1. And so we're finished. Okay, what about this one? Instead of cosine 1 over x, what if it's just cosine of x? So keep in mind, what does the graph of cosine look like? So as this pattern keeps going outward toward infinity, what number does it close in on? It never does, guys. It's always going to, no matter what, it's always going to bounce back and forth between positive and negative 1. But if it never closes in on one single number, we can't say that this limit exists, because it never develops a close-in pattern. This limit does not exist. Remember, the piece that we've been looking at says if you take the limit as x approaches infinity and you actually do get some kind of a number like this one, this is telling us this particular graph will have the horizontal asymptote y equals 1. Because our limit approaching infinity actually does equal some finite number, it must have a horizontal asymptote. Our previous one, when we were looking at this and we said this particular one went upward to infinity, well, if this is going up to infinity, this will not have a horizontal asymptote. Same thing here. Does cosine of x have a horizontal asymptote? Since it does not have a horizontal asymptote, we cannot have this limit exist. Okay, what about these ones? What's your intuition based on them? Well, if we're taking really big number like a million cubed is even bigger than a million. So just on intuition, that should be going toward infinity. And what about this one? Yeah. So quick pieces. They're not always going to have to be doing the full algebraic component. A lot of times, just logical thought will tell you what some of them are going to go to. These ones are good prime examples of them. What about this one? Well, we could look at this and say, if we're trying to do infinity cubed and subtract infinity, well, infinity cubed is infinity, so we're still looking at it and saying, that doesn't make any sense. Whenever you have addition and subtraction, it is frequently better to turn it into multiplication. We could factor that out and say, like this. And in this instance, we could then split this up in terms of a product, showing the full algebraic instead of just the intuition version. What's the limit of x? Infinity, multiplied. And so this would be the full version showing why it actually will be infinity. Your immediate intuition, of course, was correct, because you guys probably knew the general shape of that function would be something like that. Actually, I think it's more like that a little bit. But still, as x is approaching positive infinity, the y value is going up to infinity. All right, so what is your suspicion on this one? I'm going to start by writing it out so that we have a decreasing or a descending order. Well, pay attention to the exponents. It's not 2 matching 2, so that quick shortcut we had before is not going to work. If we tried direct substitution, infinity cubed plus infinity, we wind up with infinity over infinity, which doesn't make any kind of sense. This is a problem that is greatly benefited by that divide out by the largest exponent that we did before. And I'm going to skip some of the algebraic steps, but we'd have x cubed plus x over x squared plus 4 over x squared. But this technique that we did before, the largest exponent in the denominator. Okay? This would be a piece then that would give us x cubed over x plus x over x squared over x squared over x squared plus 4 over x squared. And we're still taking the limit as x is approaching 1, infinity. And you'll see why I wanted to use the largest exponent from the denominator here in a second. So that gives us, what's x cubed over x squared? That part becomes just x. X over x squared, 1 over x. X squared over x squared is 1. All right, so when we're trying to do direct substitution now for our approach, for our limit, 1 over x is 0. 4 over x squared is 0. So we're taking the limit of x over 1 that's infinity. Important observation to make here. The degree of the numerator is larger than the degree of the denominator. Whenever you wind up with the numerator degree larger than the denominator degree, your limit is going to equal infinity. Similar problem here, where we would have limit x approaches infinity, x minus 2 over x squared plus 4. And so we're going to take all of them over the x squared term, which would allow us to write this, and I'm going to skip the algebraic step here, but we'd have x over x squared minus 2 over x squared over x squared over x squared plus 4 over x squared. Well, when we start looking at each of these pieces, what are all of them going to? What is x over x squared approaching? Well, that's going to be 1 over x. 1 over x, you're correct, is going to 0. 2 over x squared, that's 0. X squared over x squared, that's 1. And 4 over x squared, that's also going to 0. So we're looking 0 minus 0 over 1 minus 0. Piece that we would note, the degree of the numerator is less than the degree of the denominator, so it's 0. In pre-calculus, they probably gave you this rule and said, hey, here's this cool rule you get to use for the end behavior model, but they didn't really go through and explain why it works. This step of dividing out by the largest exponent in the denominator is the calculus reason why your pre-calculus shortcut worked. You should be able to do this work. It's okay to use the shortcut, but you should still be able to use it, the work, and show why it's true also. Okay, sketch the graph of by finding its intercepts and its limits as x approaches positive or negative infinity. So consider this part. Let's get the intercepts right away. Our intercepts, remember, are where we're crossing the x-axis. Those would occur where y is equal to 0. Well, isn't it wonderful that it's already in factored form? So x minus 2 to the 4th would tell us we have a 0 at x minus 2, or rather at x equals 2. Likewise, x plus 1 cubed tells us we have a 0 at negative 1, and we would also have a 0 at positive 1. Well, we know that this is going to be a polynomial. If we factored it out or distributed it and completely expanded it, it's a polynomial, so it has to be continuous. But now what does it look like? We've got 3 points, which is nice, but we need more information. So let's consider the limits at infinity. If we're taking x approaches infinity, infinity minus 2, infinity to the 4th, infinity plus 1, infinity. So what does this thing go into? That will approach infinity as x approaches infinity, which is telling us that somehow we need to wind up all the way up here, so chances are pretty good it's going to have to come down like that. But do we know if we go across, do we come back up? We don't know if this comes down and just barely touches it and turns around. There is some other missing information that we would need. But we know we have to wind up in this area anyhow. Okay, let's take x approaches negative infinity. Negative infinity minus 2, negative infinity. To the 4th power, what happens when you multiply 4 negatives? This is going to go to positive infinity. Infinity, negative infinity plus 1 is negative infinity. You cube it, this is going to negative infinity. And then negative infinity minus 1. So positive times negative times negative. This should be also approaching a positive infinity, so we need to have something that looks like this. In your pre-calc, do you remember doing multiplicity? What does the even exponent of 4 tell you? The even exponent of 4 would tell you that it comes down and just touches it and comes back up. The odd exponent tells you it has to cross through. And then the odd exponent of 1 also tells you it has to cross through. So we would have something like this, and we have no idea how high these peaks go. If we wanted to know how high this comes up, or how far down, if we wanted to know how high this comes up or how far down that goes, we could use the first derivative test or the second derivative test to figure out where our relative maximum or minimum should be, and then set the derivative equal to 0. We could continue this problem further. That's actually one of our topics that we'll have upcoming, but for this problem, here's a quick sketch. Now, to finish up our study with the limits at infinity, we should take a quick look at the formal, precise definition. You should note that this is stuff that is very similar to our previous epsilon delta definitions, or more specifically, similar to our limits at infinity, or our infinite limits. But the short version is this graph at the bottom. We would say that the limit as x approaches infinity is equal to some finite number L. Well, if we're looking at a finite height, it's possible to get a plus and minus height, which is where we're getting our plus minus epsilon that we had before. And we've already discussed in our previous sections why, when we're taking f of x plus or minus epsilon, that's going to be above or below. That's basically how we would write that idea up. We've already seen how the absolute value tells us that. And so our limit at infinity is just saying this notation means there will be some x value, which we are going to call capital number N, so that if you go past this big number N, you will be able to crush in on the height and keep the function inside the plus minus bounds of epsilon. And it's the exact same thing if we're doing this to the left as well. If we want a limit at negative infinity, if you go beyond some negative number n, it will force you to be within the bounds of L plus epsilon or L minus epsilon. Very, very similar to our epsilon delta definition, except since we're going out toward infinity or negative infinity, we don't have a plus delta minus delta. It's just a way of saying go to the left, you get trapped in this band for plus or minus epsilon. So use a graph to find a number n such that if we have x is bigger than n, then this whole piece. Well, I would like to point out something here. You notice how we have 2 and 2? Because the exponents match, we've got our shortcut that would say the limit is just 3 over 5. That's where the 0.6 is coming from. 3 over 5 is our 0.6. So this is telling us we need a graph. Well, let's grab our calculator and plug it in. And here is the graph entered in the standard window. Well, we know our epsilon is 0.1 and the limit is 0.6. So if we're going to go plus or minus the epsilon, that would wind up being 0.6 plus epsilon, which is of course going to be just 0.7. Or we would also have 0.6 minus epsilon, which we know will just be 0.5. Well, looking at this particular thing, you see that, and this is really difficult to see. So let's change our window. Window, settings, and I'm going to say an x minimum of 0, an x maximum. I suppose we can leave it at 10 for now. I don't know if we're going to need to change it. But our y minimum, let's make it 0.4. The y maximum is 0.8. And I'm picking those just so that we still have our 0.5 to 0.7 range in there and still have enough room so that we can put these other pieces around. So, at which point, which capital N, where do we reach a number that's going to put our square root inside these bounds? Well, that number is right where the intersection is. So we can go into menu, analyze graph, intersection, graph 1, graph 2, lower bound, upper bound, and it gives us our intersection of 6.74. We know that's potentially rounded, and so if we were looking for some capital N, that if we have any x value that is beyond this number, well, our intersection says anything to the right of that would work. But since this is rounded, let's just do an even bigger round and say instead of 6.74, if we were to take an x value right around 7, well, if you're at 7, if you go to the right of 7, you're still in this window. So we could use the graph, just take the intersection, gave us n is about 6.74. Let's just round it up and say 7. We're done. Lastly, use the definition to prove that the limit as x approaches infinity of 1 over x actually is 0. Okay, so remember what the definition says. The definition says for every epsilon greater than 0, so we will say take any epsilon greater than 0. The definition continues by saying there is a corresponding number n such that if x is greater than n, so we can then say suppose that x is greater than n. I'm sorry, that's my negative infinity. So x is greater than n. All right, so we will now look and say, consider absolute value of f of x minus L. Well, please note that this is saying 1 over x minus 0. That's equal to just the absolute value of 1 over x. And since we are considering x numbers approaching infinity, for any x value that's greater than 0, we get this is just 1 over x. Remember what we need. We need 1 over x to be less than our epsilon. Well, this piece, we can say that this is less than 1 over x with its greatest integer. Just telling it to round up. Consider why this works. If we had a number that's like 1 over 6.7132, if we rounded 6.7132 up to the next greatest integer, that would be 1 over 7. Well, we're dividing by a larger number. Whenever you divide by a larger number, you get something that's bigger. Or rather, you get something that's smaller. Using the greatest integer function in this way actually is going to give us greater than. Well, we don't want greater than. We want less than. So instead of using the greatest integer function, we could actually say, take this number and round downward using the floor function. Likewise, that's saying something like 1 over 6.7. If we rounded it down to 1 over 6, instead of being greater than, 1 over 6.7 will be less than 1 over 6. Well, this is really all we need then. We've set up using the floor function. This is the piece that we now need. We need this piece to be our epsilon. But this x, using the floor function, let me backtrack this up and phrase it a little bit better. We just need this piece here to be some number that is smaller than x. Similar to the way that 6.7 and 6 have that relationship. 6 is smaller than 6.7. We don't have to use the floor function because we already have the fact right up with our initial assumption. X is greater than n, which is saying n is less than x. We already have some number that is smaller than it. Well, because n is less than x, we can say this part is true, which tells us we would have 1 over n needs to be our epsilon, so we would just take this part right there. That's epsilon. And we've got it. As long as we take 1 over n to be our epsilon, or at least round it so that we take some number that's bigger than n or smaller than n so that this works out, then we're all set. Please note our learning objectives. Evaluate a limit as it approaches positive or negative infinity. That's used to determine the end behavior. And depending on if this end behavior turns out to be a finite number, that can also give you your horizontal asymptotes.